Hey everyone, we're going to get started on a short little video about the ratio and root test. Most of the time will be spent on the ratio test, and the root test will just be a minute at the end. This is on the heels of learning about the difference between absolute and conditional convergence. We're going to see that both the ratio and the root tests are going to test for absolute convergence or divergence. And they're very useful, particularly the ratio test is very useful for tackling series that look complicated, such as this guy from yesterday. So what we're going to do is we're going to approach this as the test suggests, by looking at the proportional increase or decrease of the sequence. In particular, we're going to look at the n plus first term of the sequence divided by the nth term of the sequence. Okay? Now, remember that we don't really care about the first few terms of a series. We don't even care about the first several terms of a series. We care about the behavior toward infinity, as n approaches infinity. So let's take the limit as n approaches infinity. And I guess if we're really concerned with proportions, we don't really care about positive or negatives either. So maybe we'll consider the absolute value of an plus 1 over an. And we're just going to see what happens with this limit. So before we set criteria for convergence or divergence, let's just take a look at what happens in the previous example. The limit as n approaches infinity of, don't really need absolute values here, but let's just keep them anyway. A to the n plus 1 over n plus 2 over 5 times 2 times the quantity n plus 1 plus 1, right? You see we're taking the n plus first term of that series, or sequence, if you will, and we're not going to divide fractions this complicated. It's a terrible idea. We're going to multiply by the reciprocal. And here, this just means writing a sub n with the denominator now in the numerator, and the numerator now in the denominator, right? This part shouldn't take any thought. Okay, now I'm going to drop the absolute value signs, right? Because all of our terms are positive anyway. That's just to illustrate. So we're going to have the limit as n approaches infinity. Now, what I strongly recommend doing, I guess we don't need the absolute value signs, is grouping the terms, the like terms, right? So put 8 to the n over 1 over 8 to the n times n plus 1 over n plus 2 times 5 to the 2n plus 1 over 5 to the 2n plus 3, right? You see I simplified that from 2 times the quantity n plus 1 plus 1. Be a little careful with that. And now, you can see that stuff's going to cancel out pretty nicely. That really just becomes 2 right there, right? And now if we think about it, what happens as n approaches infinity of n plus 1 over n plus 2? Well, it really just goes to 1. You can just say that right now. Just say, goes to 1. Okay? So what we're going to get here is an answer of 8 over 5 squared, or 8/25. So as n gets large, each term is roughly 8/25 as big as the term before it. Maybe I'll just put a little squiggly. Roughly 8/25 as big. All right. And as it turns out, this means that our series is getting smaller and smaller, or the terms of our series are getting smaller and smaller enough that it's going to converge. Hopefully that makes some amount of intuitive sense. So fact 1, let's state the ratio test. The ratio test says the following. 3 possible scenarios, right? If we take the limit as n approaches infinity of the absolute value of the n plus first term over the nth term, and we get that it's less than 1, strictly less than 1, then the series is absolutely convergent. Now that should make sense that it's absolutely convergent, right? Because we took the absolute value of the term straight up, right? Even if it has an alternating term, you could use the ratio test without the negative 1 to the n and get the same result. If, on the other hand, we find the ratio of the n plus first term to the nth term as n gets large, and it's greater than 1, strictly greater than 1, or if it winds up being infinite, then the series is divergent. Right? Because each general term in the series, or in the sequence, I should say, is getting bigger and bigger than the previous term. And so you're adding something bigger and bigger and bigger each time. The third criterion is maybe a little interesting, perhaps, maybe a little counterintuitive. If the limit equals 1, then we don't know anything. We have no idea whether it converges or diverges. It could be either. It means you shouldn't have used the ratio test. Use another test. Okay? Ratio test equals 1. You're kind of SOL there. So because our previous limit was 8/25, which is less than 1, our series is absolutely convergent. Okay? Perhaps looking at it, one way that maybe you could see that's true is if you were really clever about it, maybe you could have compared it to a convergent geometric series. Now, one nice thing about the ratio test is it allows us to consider other kinds of series that use a certain term called factorial. N factorial, which is written, it's said as n factorial equals n times n times n minus 1 times n minus 2 times blah, 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 times 3 times 2 times 1. So if you just try a couple of examples, a couple of numbers, you'll see this term grows really, really quickly. N factorial, we may have just brought this up out of nowhere, but I promise you we're going to use it in, in a little while. N factorial is the number of ways to order n distinct objects, like lining up n different people in a row, or permuting the numbers 1 through n. In particular, that means that 0 factorial equals 1, right? There's one way to order 0 objects, right? This way, right? Just look at the nothing in front of you. That's the one way to order it. So the ratio test is useful anytime you see a factorial in your general term. It's also useful anytime you see an exponential term. So I'm going to leave example 2 to you. And I will just say that if a series general term ever looks really complicated, there's a good chance the ratio test will handle it just fine, and that it won't be quite as complicated as you think. So try example 3, and maybe try example 4 as well. And let's spend a minute on the last page looking at the root test, which you could say is the the nth level of the ratio test in a sense. So if we take the same approach, but instead of proportionally considering the absolute value, we consider the nth root of the absolute value of the general term, and we get that that is less than 1, then the series is absolutely convergent. And that means that as n is getting bigger and bigger and bigger, the general term is getting exponentially smaller in some way. If, on the other hand, the term is getting exponentially bigger, well, you might imagine our series is going to diverge. And if you take the nth root and you get that it equals 1, well then, once again, we don't know anything. Right? We have to, again, use a different test. So I left you an example. Example 6. Try to do that. See how it goes.